Okay, let us begin with our discussion on ellipse. Yesterday we have derived the standard equation of ellipse and got the basic properties in place. Let us continue our discussion with some additional properties. Now, y is equal to mx plus c is tangent to x square upon a square plus y square upon b square is equal to 1. Find condition for tangents. How M, C, A and B should behave so that this line is tangent to this curve. Easy. We have done it several times. Get me the condition for tangency, find the condition for tangency and point of contact. Okay. Let x1 comma y1 belong to the ellipse and we draw tangent at that point. Then our equation of tangent is x1 upon a square plus y1 upon b square minus 1 is equal to 0. Correct? And if we write equation mx minus y plus c is equal to 0 and both of them should be tangents. So both of them should be the same geometric line having two different algebraic expressions and hence their coefficients must be proportional. Therefore, x1 upon a square upon m should be equal to y1 upon b square upon minus 1 is equal to minus 1 upon c. Oh, good. Directly we got the point of contact. Therefore, x1 is equal to minus a square m by c. So, in this way, you get the point of contact first and the condition for tangency later. B square by. Now, how these x1 and y1 are? They are on ellipse. Therefore, they satisfy equation of ellipse. So, minus a square m upon c bracket square into 1 upon a square plus b square upon c bracket square into 1 upon b square is equal to 1 must satisfy, and that is what will give us condition for tangency. So a fourth m square upon a square, so a square m square upon c square plus b square upon c square is equal to 1 implies c square is equal to a square m square b square. This is condition for tangency. This is point of contact. Very easy. You can solve simultaneously and make discriminant equal to 0 to get the condition for tangency first, followed by point of contact. That could be another method of doing the same thing. But this has to be now routine for you. You need not have to think for doing all these things. It has to be basic. Okay. Good. Let me give some numbers also to these questions. Maybe today's first question, today's second question, now today's third question. Find auxiliary equation. In terms of slope. for getting tangents. To x square upon a square plus y square upon b equal to 1, passing through points x1 comma y. x1 comma y1 is any point in the plane. You want tangents to be drawn, so you need slope. So which auxiliary equation will you solve to get the slopes? Y is equal to mx plus minus under root a square m square plus b square, because we have found out c is equal to radical this. So this is the line which is going to be tangent to ellipse, and what we are asked to do is that this line should pass through x1 y1, and therefore y1 minus mx1 is equal to radical a square m square plus b square. This should give us quadratic in m square inside bracket x1 square minus a square minus 2a minus 2x1 y1 m plus y1 square minus b square is equal to 0. This is your quadratic equation, which if you solve, you will get two slopes and you will get two tangents. Condition. Now what is the product of the roots in this case? Product of the roots is y1 square minus b square upon x1 square minus a square, correct? This is product of the slopes. And if you happen to make them minus 1 product, so in what is then, this is the special case when both the tangents are perpendicular to each other. What is that you get? Then we will get relationship of x1 comma y1. It's a basically it is going to be the point of intersection of perpendicular tangents. So it's a locus. So locus of point of intersection of perpendicular tangents is this, which is y1 square minus b square plus x1 square minus a square is equal to 0. Implies replacing x1 and y1 by x and y respectively, we get x square plus y square is equal to a square plus b square. Oh, this is circle. So locus of perpendicular tangents to given ellipse is a circle and is known as director circle. And the radius of that is radical a square plus b square. So it's going to be a radical x square plus b square, some circle outside this ellipse, from where if you happen to draw two tangents, they are going to be perpendicular. It is that easy. One after the other, there is a chain by which you derive all the properties of these conic sections. समझ लें डायरेक्टर सर्कल. In case of parabola, it was straight line. Directrix, director circle. So you understand those names also. It was a line there for directrix. Otherwise that line is a director circle of parabola, because locus of point of intersection of perpendicular tangents. In case of circle, it is what? It is yet another concentric circle, director circle, isn't it? From perpendicular tangents, you want perpendicular tangents. It is going to be something root 2. 2. If this is x square plus y square is equal to a square, original given circle, then you must get this square, correct? So what should be the radius of director circle? X square plus y square is equal to 2a square, correct? नहीं. Yes.
Oh, sir.
Yes.
Yes.
Root 2 times root 2 square. In case of circle, it is this circle. Now you will keep looking at the symmetry. When A becomes B, our B square was A square into 1 minus E square. Correct? When B square becomes A square, practically E becomes 0. It's a limiting case. So suppose if you assume E little greater than 0, E is little greater. See now, okay, कुठे चाललोय मी पण ठीक आहे सांगतो तुम्हाला. This is S and your directrix, suppose this is S and directrix is here. So if your E is equal to 1 here, correct? Halfway distance between directrix and focus. Halfway distance E is equal to 1. SA upon AZ is 1. So this A moves near S. Okay, our eccentricity decreases. Suppose S and A are so close, they are not coincident but very, very close, so that E becomes very small, 0.000 something, 1. In other words, it means these directrix are far away. They are the lines at infinity. And when S coincides with A, both the sides, both the directrix go to infinity because E becomes 0, B square is equal to A square, and you happen to get that circle. And the ratio of compression, which is B upon A, becomes 1. There is no compression. And that is what I can show you here, because if I replace B by A, I get director circle of circle. So ellipse, circle is special ellipse. You can say that. Circle is a special ellipse. But anyway, don't get into that so early. And we will continue our properties. Property number next 4. Green. 4 number property, what I should give you is T is equal to 0. We already know all 4 interpretations. Okay, fine. Pole of y is equal to mx plus c. E is going to be same, whatever you have found out, minus a square m by c comma b square by c. This is going to be pole. Polar duality is also going to work because they are the results which are common to any conic section. Joint polar duality, I will just mention them because you need to use those results for every conic section. So polar duality, 7, joint equation of tangents, which is t square is equal to ss1. 8, equation of tangent in terms of midpoint, t is equal to s1. These are very common things. So maybe just to refresh and to get the idea about how this goes, let me give you one ellipse. I have not given you any ellipse so far. X square upon 25 plus y square upon 9 is equal to 1. Suppose this is ellipse, and inside I go 3 units on the x-axis and 1 unit on y-axis. Okay, M is supposed to be midpoint of the chord. This is ellipse 5, 3. Minor axis, length of minor axis is 2 times B, which is 6. This is 6. And this is 10. Okay, then this is 10, therefore point is somewhere here. And we want an equation of chord such that that point is middle. खड़ा हो गया. Find the equation of normal at px1 y1 and your ellipse is same, x square 2, x square upon a square plus y square upon b square is equal to 1. Okay, खड़ा. You know equation of tangent, therefore you know slope of tangent, m1 m2 minus 1, therefore you know slope of normal. This is the slope of normal. If this is the slope of normal, what am I doing here is, suppose you give me slope of normal 3 by 7. Then I will start writing equation of line 3x minus 7y. That is my LHS. And if you have a point on that normal, you put it in this and write on RHS. That is how it has to be done very fast, very quickly. So the slope is a square y1 upon b square x1. So I write the equation of normal like this: a square y1 times x minus b square x1 times y is equal to. And now I know that the point is on the line, therefore it must satisfy the LHS. So I put it in RHS. x1 y1 comes common out, goes in the denominator, and therefore it is an equation which is easy to remember. Basically synergic with the equation of ellipse and tangent. Then at p theta, find the equation of normal at p theta. Cosmetic changes. Okay, replacing x1 by a cos theta minus b square y by b sin theta is equal to a square minus b square. So equation of normal in terms of parameter theta is a gets cancelled, so ax upon cos theta minus by upon sin theta is equal to a square minus b square. Very good. Next, find the equation of normal in terms of slope. M. That means what I am asking you to do is y is equal to mx plus c is normal. So find the condition of normalcy, etc. Find equation of normal in terms of slope m. Our one way of writing equation of normal, we have already written a square upon x1 times x minus b square upon y1 times y minus a square plus b square is equal to 0. This is one normal, and what we are saying now is this is another normal. Mx minus y plus c is equal to 0. So both these are normals, therefore their coefficients must be proportional, and hence a square upon x1 m should be equal to b square upon y1 into minus minus gone. So b square upon y1, which is equal to b square minus a square upon c. That gives us x1. x1 is equal to, now we cannot use these two ratios because they will be in terms of each other, but we have another ratio which is constant. So x1 is equal to ca square upon m into b square minus a square. Correct? And y1 is equal to, these are the points, foot of normals. This is foot of normal because x1, y1 is on the curve. So y1 is equal to cb square on b square minus a square. And these are the points on given ellipse. Therefore, they should satisfy equation of ellipse. So ca square bracket square upon m square into b square minus a square bracket square. So this is x 1 square into 1 upon a square plus cb square bracket square upon b square minus a square bracket square. This is y1 square into 1 upon b square should be equal to 1. Correct? I think so. So what is the simplification? C square a square. A square is 1. Denominator of everything you can make a square m square a square b square m square into b square minus a square bracket square. If this is our LCM, then c square a square from here, no, oh sorry,
Sir, a square b square cut हो
1. So c square a square, c square a square, correct chale, plus c square b square from here, and you require m square because m is not there in the denominator, is equal to 1, which implies c square inside bracket a square plus b square m square is equal to m square inside bracket b square minus a square bracket square. And hence c square is equal to, or maybe c is equal to, taking root simultaneously, plus or minus m inside bracket b square minus a square, or a square minus b square, because this plus and minus is available outside, and it becomes radical a square plus b square m. This is your condition for tangency, and therefore equation of normal in terms of slope is equal to y is equal to mx plus minus m into b square minus a square upon radical a square plus b square m square. And the points of contact we have already found out. These are the feet of normal or foot of normal. Write down those who have not done it. Next, find the auxiliary equation in terms of slope. That means if point x1, y1 not on the ellipse, somewhere else is given, how you will find equations of normals. That equation we need to find in terms of slope. Okay, if you simplify this and put x is equal to x1 and y is equal to y1 in the above expression and write it in the expanded form, you will get it m raised to 4 times something plus m raised to 3 times something plus m raised to 2 times something is equal to 0. Something of this fourth degree equation. And then how is this auxiliary equation helping us? Suppose if at all you want to find out the normals passing through this point, then this auxiliary equation tells us how to get those slopes. That is the first use of this auxiliary equation. All the slopes, once you solve this fourth degree equation, you will get all the 4 slopes. and hence you will get all the four lines. So maybe there will be one tangent here, one normal here, maybe there will be another normal here, maybe there will be some normal, difficult to imagine, but okay, some normal here, some normal here, there will be some normal again here, and there will be some normal this side somewhere here. So you will get to know these slopes m1, m2, m3, m4, and you get those. That is first. Second, it is telling us this power 4 here is telling us that there will be 4 normals. If the point is very well behaved, then there will be 4 normals. And then depending upon the position of that point with respect to the ellipse, the easiest 4 normals that I can show you are from origin to standard ellipse. This is origin, so this is one normal, this is another normal, this is another normal, and this is another normal. There are 4 normals, and therefore this degree of this m polynomial is important. 4 normals we get. Okay. Now geometrically, understand this experiment by which you will come to know how you should get. Suppose we have ellipse. Suppose we have ellipse. Suppose we have ellipse. Somehow it is not giving me ellipse. Last try. Suppose we have ellipse. And suppose this ellipse is in a swimming pool full of water. Now you throw stone, water is still water, no waves at all. The moment you throw stone in this water, there will be circular waves which will be generated because of the stone. And then you observe that those circles, these circles will first touch here. Oh, this is one of the normals. Okay, then it will grow, grow, and then this circle will touch again somewhere here. This is another normal. Then it will further grow, and maybe it will touch somewhere here. I am not sure about the geometry part, but suppose here. And then again they will grow, the circles will grow. Even if your swimming pool is small, and circles will continue to grow. And then you will find that it is tangent here. So this is another normal. That is how, if at all you want to draw normals to an ellipse, this is the procedure. You should go to swimming pool and observe and then get those points geometrically. If you want algebraically, then I think we should be able to find out the points, feet of normals. We will see how to go about it. But this is geometry. How are you going to really locate? And once you start imagining it this way, you will realize that yes, if the stone is thrown to the correct point, there will be 4 normals. If it is at the center, then 2 circles internally touching will give you 2 points at a time simultaneously, this point and this point. Circle is thrown here, say stone is thrown here, and then there will be 2 circles which will be from outside tangent, and it will give you the remaining 2 feet of normals, and hence this is it. Now depending upon, suppose you throw stone outside, then there will be first circle which will be tangent like this, so there will be a foot of normal here, and there will be another circle maybe which is something like this somewhere, and you will end up getting one more foot of normal, and then remaining 2 are gone, not possible. 4th degree equation, maybe having 2 real roots and 2 imaginary roots. So imaginary points you will not get. but I mean, advanced study of ellipse, we will be able to find out what is the region inside ellipse, which in that region, if we take a point, we get four distinct normals. That is what we can actually find out in syllabus. We will not do it, but yes, there some calculations can be done so that the region inside ellipse you can specify and you will get four distinct. Oh, if the point is on the ellipse, the first normal is that point itself, and maybe you can draw two more. Difficult to draw four. So it all depends upon what this equation is. Can it be factorized? Can it be factorized into a1m square plus b1m plus c1 into a2m square plus b2m plus c2 kind of factorization? Is it possible? Then after factorization, are these reducible quadratic or they are irreducible quadratic? So if they are all four, if we can make it in looking like this, m1 minus m minus constant 1, m minus constant 2, m minus constant 3, m minus constant 4, then these are the slopes, all good, but you may work it out and find out how many normals. Okay, it is huge calculation. So unless and until your numbers are good in the given ellipse, calculations are very complicated. Okay, but related to this, let me give you 13th problem. Prove that in general, four normals can be drawn in general. Four normals can be drawn from any point. Where is my cursor? Why is cursor behaving badly? Can be drawn from any point to an ellipse and that the sum of eccentric angles of their feet is equal to an odd multiple of two right angles. That is 180. Odd multiple of 180 is a sum of eccentric angles. First of all, we are supposed to do something related to eccentric angle and normal. Therefore, do we have equation of normal in terms at p theta? Yes, this is the equation x square ax upon cos theta. Okay, I am going there. Ax upon cos theta (57% is correct. Ax upon cos theta minus by upon sin theta is equal to a square minus b square. Now can we write a square e square for a square minus b square? Yes. So that will be a little smaller than a square minus b square. Okay, so this is theta is our eccentric angle, and it is all these four lines are passing through, say, h comma k. Let h comma k be point through which all normals are possible. So they are co-normal points. Co-normal points. These feet will be co-normal points. They all of them are concurrent. All normals are concurrent at h comma k, and therefore ah upon cos theta minus bk upon sin theta is equal to a square e square is our equation. Now we have to exploit trigonometry. Tan theta by 2 is equal to t. Therefore cos theta is equal to 1 minus t square upon 1 plus t square. Sin theta is equal to 2t upon 1 plus t square. Okay, this is our trigonometry. We know theta is our eccentric angle, but trigonometry is true, and hence by substituting here, what we are going to get is ah upon cos theta. So into 1 plus t square upon 1 minus t square. That is cos theta minus bk to sin theta, which is 1 plus t square upon 2t is equal to a square e square. Now you clear the denominator and you will get equation in T4. Write down that equation equal to 0. Okay, that is first part of the story that we need to complete, and then write down the expansion. Then we can find out what is sigma 1, sigma 2, sigma 3 of this T4th equation. But then more than that, what we are supposed to do is write down the expression for tan of theta 1 by 2 plus theta 2 by 2 plus theta 3 by 2 plus theta 4 by 2. Why do we require this expansion? Is because we are supposed to prove sum of eccentric angles of their field is equal to odd multiple of 180. 2n plus 1, odd multiple of 180. Okay. So odd multiple of 90, tan is undefined. That is what we know. So if the result is true, odd multiple of half angles should give us an undefined RHS. Undefined RHS. This and try to put these numbers, which is sigma 1, sigma 2, sigma 3, etc. Because what is t? T is tan theta by 2, right? Tan theta by 2. And maybe theta 1, theta 2, theta 3, theta 4 are the roots of this 4 degree. I think I have told you everything to do, and you should come out with final proof saying that yes, they are odd multiple of 180. Okay, so the fourth degree in T I will write directly, and it looks like this: T4 into BK plus 2T cube into AH plus A square E square plus 2T into AH minus A square E square minus BK. Can you confirm this? Is it correct? This is important equation. It gives us
Yes, sir.
lot of information. First information that we get is sigma 1, that is T1 plus T1 plus T2 plus T3 plus T4 is equal to minus 2 into AH plus A square E square divided by BK. This is sigma 1. Sigma 2 happens to be 0. This is sigma 1. Sigma 2 happens to be 0 because there is no term of T square, and sigma 3 is AH. Now this is minus, so minus 2AH minus A square E square. I don't know whether this is required or not, but we have to calculate BK, and sigma 4 is equal to minus 1 BK upon BK. These are the interesting facts about this fourth degree equation in T. Now I have asked you to expand this summation of 4 angles and tan of it. Then you will end up getting sigma tan theta 1 by 2. That means theta 1 by 2, tan theta 1 by 2 plus tan theta 2 by 2. That is your first term in numerator, minus second term in numerator is sigma tan theta 1 by 2 tan theta 2 by 2 tan theta 3 by 2 plus 3 at a time, all of them. Sigma takes care of that. This is what is your numerator. Denominator you have 1 minus sigma tan theta 1 by 2 tan theta 2 by 2, 2 at a time, plus 4 at a time, all of them. Tan theta 1 by 2, tan theta 2 by 2, tan theta 3 by 2, tan theta 4 by 2. So this is now, this is our what already the information that we have. So numerator sigma T1 plus T2 is tan theta. So is this sigma 1, first bracket? Why I have written it as S1? Sigma 1 minus sigma 3 upon 1 minus sigma 2, which is 0, and this is sigma 4 minus 1. So sigma 1 minus sigma 3 upon 0 is tan of this. I mean, we should not write it like this, but I am showing that this is odd multiple of 90. That directly implies, sum of, that is, this implies theta 1 plus theta 2 plus theta 3 plus theta 4 upon 2 is 2n plus 1 into 90 is equal to proof. Okay, so this is what is the proof of sum of eccentric angles of conormal points is odd multiple of 90. Next problem, a chord of an ellipse subtends 90 degree at its center. Show that it touches a circle. Concentric with ellipse. Okay, this is I mean, there are more than one ways of solving this. I might solve by one method, you solve by whatever method you think right. It can be done using trigonometric form of the chord, or you do it otherwise also, but I will prefer to do it using. And therefore, if eccentric angle of P is theta and eccentric angle of Q is phi, these are the 2 points on the ellipse, theta, P, and it is supposed to be 90 degree at origin. So Q is phi, P is theta. Then what is the equation of chord? We have derived it yesterday. X upon A cos of theta plus phi by 2 plus y upon B sin theta plus phi upon 2 is equal to cos of theta minus phi upon 2, right? And this is homogenization problem because you are supposed to have angle at center equal to 90 degree. And this is the equation of chord that you have. Therefore, what you are supposed to do is solve, homogenize with the ellipse. X square upon a square plus y square upon b square plus or maybe minus 1 is to be replaced by x upon a cos theta plus phi by 2 plus y upon b sin theta plus phi by 2. This is your numerator, and the denominator is cos of theta minus phi by 2. This is 1, but we need 1 square. I mean, we need to homogenize. Therefore, we need power of this entire thing. 2 is equal to 0. This is the joint equation of the lines passing through intersection of chord P and Q and origin. And then what is the condition? If they are supposed to be perpendicular, then coefficient of x square and y square should be added to 0. So let us try to collect the coefficient of x square. Coefficient of x square, 1 upon a square minus, what is this? This upon this bracket square. So cos square theta plus phi upon 2 upon, we have a also here, so a square cos theta minus phi upon 2 theta square, this is coefficient of x square, right, plus 1 upon b square minus sine square. This should be equal to 0, correct? So if this is equal to 0, by looking at this expression, we should conclude that there exists circle. What is supposed to be proved? That it touches the circle concentric with ellipse. So, this is our chord and it is supposed to touch the circle concentric with ellipse. Then the circle is going to look like, we can find out now how the circle should look like. if it is tangent. So from what is the distance of this line from origin? We can find out that distance of D is equal to, or maybe D square is equal to, yeah, better. This numerator you put 0, so these two terms are gone, and you have cos theta minus phi upon 2 bracket square, that is what is your numerator, and in the denominator you have, actually you have radical, but that radical is gone because of the square. In the denominator you have a square plus b square, so cos square theta plus phi by 2 plus upon a square plus sine square theta plus phi by 2 on b square. This is our denominator, and with this expression that you have with you, can you show that this is constant? And you will observe that after just one simplification, this cos square theta minus is available in the denominator. What you should do is just take this cos square upon a square is also is it the reciprocal of this with 1 upon a square and 1 upon b square on RHS? Can you see that? Is this d square reciprocal of these two terms added? I mean, if they are added, okay, let me finish. 1 upon a square plus 1 upon b square is equal to cos square theta plus something plus this minus sine square minus sine square cos square बरोबर चालेल ना cos square this upon a square minus sine square bracket upon b square whole divided by cos square theta minus phi upon 2. Correct? So if you take reciprocal of this, it is this, and it is constant. Therefore, there exists a circle touching this, all the chords, which subtend 90 degree at the center. Is it clear?